Everyone, welcome back. I'm your friend Inside. So today we're going to learn the
Logarithms.
logarithms.
Let's learn a little bit about the wonderful world of logarithms. So we already know how to take exponents. If I were to say 2 to the 4th power, what does that mean? Well, that means 2 times 2 times 2 times 2. 2 multiplied or repeatedly multiplied 4 times. And so this is going to be 2 times 2 is 4, times 2 is 8, times 2 is 16. But what if we think about things in another way? What if we know that we get to 16 when we raise 2 to some power, and we want to know what that power is. So for example, let's say that I start with 2, and I say I'm raising it to some power. What does that power have to be to get 16? Well, we just figured that out. X would have to be 4. And this is what logarithms are fundamentally about. Figuring out what power you have to raise to get another number. Now, the way that we would denote this with logarithm notation is we would say log base, actually let me make it a little bit more colorful. Log base 2, logs, I'll do this 2 in blue, log base 2 of 16 is equal to what? Or is equal of 16 of 16 of 16.
Right. Hi guys, why I pause a video here? Well, for this thing in this video or for this moment, the most important thing that you could know is called how can you read the log function or how can you read the log expression? Well, you could say okay. Now, for this expression, well, how can you read it? You read it as log base 2 of 16. And if you have something like this, how do you read it? You say log base A of B.
16 is equal to what? Or is equal, in this case, since we have the x there, is equal to x. This and this are completely equivalent statements. This is saying, hey, well, if I take 2 to some x power, I get 16. This is saying, what power do I need to raise 2 to get 16? And I'm going to set that to be equal to x. And you would say, well, you got to raise it to the 4th power. Once again, x is equal to 4. So with that out of the way, let's try more examples of evaluating logarithmic expressions. So let's say you had log base 3 of 81. What would this evaluate to? Well, just as a reminder, this evaluates to the power we have to raise 3 to.
Here's another sentence that we should know or we could know. Well, but sometimes if I want to expression, how can we get the value of this? I would say, well, what's the value of this expression? But to be more appropriate, we should say how this evaluate to or what this evaluate to. If you don't believe me, let me just go back for a little bit. Okay, here we go. What would this evaluate to? What would this evaluate to? You know, in Python, there's a language called Python. There has a programming language called Python, and they got a built-in function called evalue, if I remember it correct. And what that function does is to get the output of an expression, and of course, it's written in Python.
What would this evaluate to? Well, just as a reminder, this evaluates to the power we have to raise 3 to get to 81. So if you want to, you could set this to be equal to an x. Set that to be equal to an x, and you can restate this equation as 3 to the x power. 3 to the x power is equal to 81. Why is a logarithm useful? And you'll see that it has...
Alright, here he just said another point of knowledge. Well, what you could do when you say such an expression is to convert it into a form of this one, and they are somehow identical to each other. For example, the 3 here becomes the base right in here, and the x as the output becomes the exponent of that base, and this value becomes this value. They have relationship to each other.
Very interesting properties later on. But you didn't necessarily have to use algebra to do it this way, to say that the x is the power that you raise 3 to get to 81. You had to use algebra here. While with just a straight up logarithmic expression, you didn't really have to use any algebra. We didn't have to set it equal to x. We could just say this evaluates to the power I need to raise 3 to get to 81. The power I need to raise 3 to get to 81. Well, what power do you have to raise 3 to get to 81? Well, let's experiment a little bit. So 3 to the first power is just 3. 3 to the second power is 9. 3 to the third power is 27. 3 to the fourth power, 27 times 3 is equal to 81. 3 to the fourth power is equal to 81. X is equal to 4. So we could say log base 3 of 81 is equal to, I'll do this in the color I've used almost every color, is equal to 4. Let's do several more of these examples, and I really encourage you to give a shot on your own now that we get, and you'll hopefully get the hang of it. So let's try a little larger number. Let's say we want to take log base 6 of 216. What will this evaluate to? Well, we're asking ourselves, what power do we have to raise 6 to get to 216? 6 to the first power is 6. 6 to the second power is 36. 36 times 6 is 216. This is equal to 216. So this is 6 to the third power is equal to 216. So if someone says, what power do I have to raise 6 to, this base here, to get to 216? Well, that's just going to be equal to 3. 6 to the third power is equal to 216. Let's try another one. Let's say I had, log base 2 of 64. So what does this evaluate to? Well, once again, we're asking ourselves, or this will evaluate to the exponent that I have to raise this base to, and you do this as this little subscript right here, the exponent that I have to raise 2 to get to 64. So 2 to the first power is 2, 2 to the second power is 4, 8, 16, 32, 64. So this right over here is 2 to the sixth power is equal to 64. So when you evaluate this expression, you say, what power do I have to raise 2 to get to 64? Well, I have to raise it to the sixth power. Let's do a slightly more straightforward one. Or maybe this will be less straightforward, depending on how you view it. What is log base 100 of 1? You think about that for a second. And this 1, so the 100 is a subscript, and then it's log base 100 of 1. That's one way to think about it. I could put a parentheses around the 1. What does this evaluate to? Well, this is asking ourselves, or we would evaluate this as, what power do I have to raise 10 what power do I have to raise 100 to get to 1? So let me write this down as an equation. So if I set this to be equal to x, this is literally saying 100 to what power is equal to 1? Well, anything to the 0th power is equal to 1. So in this case, x is equal to 0. So log base 100 of 1 is going to be equal to 0. Log base anything of 1 is going to be equal to 0, because anything to the 0th power, and we're not talking about 0 here, anything to the 0th power that's not 0 is going to be equal to 1.
Even though he just did so much practice out there, but I still think we probably do not have a clear way to get out the results, or to get the result out.
Let's give ourselves a little bit more practice with logarithms. So just as a little bit of review, let's evaluate log base 2 of 8. What does this evaluate to? Well, it's asking us, or it will evaluate to the power that I have to, or the exponent that I have to raise our base to, that I have to raise 2 to get to 8. So 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. So this right over here is going to be equal to 3. Fair enough, we did examples like that in the last video. Let's do something a little bit more interesting. What is, and I'll color code it, what is log base 8? What is log base 8 of 2? Now this is interesting. I'll give you a few seconds to think about it. Well, we're asking ourselves, or this will evaluate to the exponent that I have to raise 8 to get to 2. So let's think about that in another way. So we could say 8 to some power, And that exponent that I'm raising 8 to is essentially what this logarithm would evaluate to. 8 to some power is going to be equal to 2, is going to be equal to 2. Well, if 2 to the third power is 8, 8 to the 1/3 power is equal to 2. So x is equal to 1/3. 8 to the 1/3 power is equal to 2. Or you could say the cube root of 8 is 2. So in this case, x is 1/3. This logarithm right over here will evaluate to 1/3. Fascinating. Let's mix it up a little bit more. Let's say we had the log base 2. Instead of 8, let's put a 1/8 right over here. So I'll give you a few seconds to think about that.
Yeah, as far as I say, this process start to getting tricky because you don't know how exactly what you should do to get the evaluated value or get the output of this expression. He did all of that by just guessing, and guessing is the most uncertain way of trying to solve a problem.
Well, it's asking us, or this will evaluate to, the exponent that I have to raise 2 to get to 1/8. So if we set that this is equal to x, we're essentially saying 2 to the x power is equal to 1/8, is equal to 1/8. Well, we know 2 to the third power. Let me write this down. We already know that 2 to the third power is equal to 8. If we want to get to 1/8, which is the reciprocal of 8, we just have to raise 2 to the -3 power. 2 to the -3 power is 1 over 2 to the third power, which is the same thing as 1 over 8. So, if we're asking ourselves, what exponent do we have to raise 2 to get to 1/8? Well, we have to raise it to the -3 power. So x is equal to -3. This logarithm evaluates to -3. Now let's really mix it up. What would be the log base 8 of 1/2? What does this evaluate to? Let me clean this up so that we have some space to work with. So as always, we're saying what power do I have to raise 8 to get to 1/2? So let's think about that a little bit. We already know that 8 to the 1/3 power is equal to 2. If we want the reciprocal of 2 right over here, we have to just raise 8 to the -1/3. So let me write that down. 8 to the -1/3 power is going to be equal to 1 over 8 to the 1/3 power. And we already know the cube root of 8, or 8 to the 1/3 power, is equal to 2. This is equal to 1/2. So the log base 8 of 1/2 is equal to, well, the power I have to raise 8 to get to 1/2 is -1/3, equal to -1/3. I hope you enjoyed that as much as I did.
Yeah, as I said before, he do this totally by guessing.
Rewrite the following equation in logarithmic form. So they have 100 is equal to 10 to the second power. So if we want to write the same information really in logarithmic form, we could say that the power that I need to raise 10 to get to 100 is equal to 2, or log base 10 of 100 is equal to 2. Notice these are equivalent statements. This is just in exponential form. This is in logarithmic form. This is saying the power that I need to raise 10 to get to 100 is equal to 2, which is the same thing as saying that 10 to the second power is 100. 10 to the second power is 100. And the way that I specified the base is by doing this underscore right over here. So
Okay, basically in this video, what you need to know is when you say such an expression, you would identically, or you could confidently say that it's a non-Logarithmic form. And when you say such an expression, you would confidently say that it's an exponential form. But never mind, it's just a len. Doesn't have any meaning out there.
The 3 points plotted below are on the graph of y is equal to b to the x power. Based only on these 3 points, plot the 3 corresponding points that must be on the graph of y is equal to log base b of x by clicking on the graph. So I've actually copied and pasted this problem on my little scratch pad so I can mark it up a little bit. So what is this first function? This first function is telling us, so x, and this is y is equal to b to the x power. So when x is equal to 0, y is equal to 1. When x is equal to 0, y is equal to 1. That's this point right over here. when x is equal to 1, b to the 1 power, or b to the first power is equal to 4. Y is equal to 4. So another way of thinking of this, y, or 4, is equal to b to the first power. And actually we can deduce then that b must be 4. So that's this point right over there. And then this point is telling us that b to the second power is equal to 16. So when x is equal to 2, b to the second power, y is equal to 16. Now we want to plot the 3 corresponding points on this function. So let me draw another table here. So now it's essentially the inverse function, where this is going to be x, and we want to calculate y is equal to log base b of x. And so what are the possibilities here? So what I want to do is let's take these values, because these are essentially inverse functions. Log is the inverse of exponents. So if we take the points 1, 4, 1, 4, and 16. 1, 4, and 16. 1, 4, and 16. So what is y going to be here? Y is going to be log base b of 1. So this is saying what power I need to raise b to get to 1. Well, if we assume that b is non-zero, and that's a reasonable assumption because b to different powers are non-zero, this is going to be 0 for any non-zero b. So this is going to be 0 right there over here. So we have the point 1, 0. So it's that point over there. And notice, this point corresponds to this point. We've essentially swapped the x's and y's. And in general, when you're taking an inverse, you're going to reflect over the line y is equal to x. And this is clearly a reflection over that line. Now let's look over here. When x is equal to 4, what is log base b of 4? What is the power I need to raise b to get to 4? Well, we see right over here, b to the first power is equal to 4. We already figured that out. When I take b to the first power is equal to 4. So this right over here is going to be equal to 1. So when x is equal to 4, y is equal to 1. And notice, once again, it is a reflection over the line y is equal to x. And so when x is equal to 16, then y is equal to log base b of 16, the power I need to raise b to get to 16. Well, we already know. If we take b squared, we get to 16. So this is equal to 2. So when x is equal to 16, y is equal to 2. Notice we've essentially just swapped the x and y values for each of these points, which is why this is a reflection over the line y is equal to.
Alright, so when I say this, what comes in my mind is that there has a concept in mathematics they call sometimes two function, inverse function.
Inverse function.
Alright, it's indeed called inverse function, and which is exactly the two function here. This is just one example of the inverse function, where you have, let's say, you have a function called log b a. Then you got another function called, if you function, then that means it must have an x on a variable inside of that. So if you got a log base a of b, that's how they read it. If you got a function like this, then you got another function called, I still think I made some mistake here. Let me rewrite it again. If you got a function called log base a of x, and you got another function called a to the x. No, never mind. I think I just made some mistake out there. So this is wrong. If you got an expression of this, and you got another expression, base a to the power of y equal to x. Okay, if you got two expression or two function like this, you could say that they are inverse function to each other. The constant e and the natural logarithm.
Let's say that you are desperate for $1, and so you come to me, the local loan shark, and you say, hey, I need to borrow $1 for a year. And I tell you, well, I'm in a good mood. I'm willing to lend you that $1 that you need for a year, and I will lend it to you for the low interest of 100% per year. So 100% per year. So how much would you have to pay me in a year? Well, you're going to have to pay the original principal, what I lent you, plus 100% of that. So plus one other dollar, which is clearly going to be equal to $2. Now, you say, well, gee, that's a lot to have to pay, to have to pay back twice what I borrowed, and there's a possibility that I might have the money in 6 months. What kind of a deal can you get me for that, Mr. Loan Shark? And I say, oh, gee, if you're willing to pay back in 6 months, then I'll just charge you half the interest for half the time. So you borrow $1, and so in 6 months, I will charge you 50% interest. 50% interest over 6 months. This, of course, was one year. And so how much would you have to pay? Well, you would have to pay the original principal, what you borrowed, the $1, plus 50% of that $1. So plus 0.50, and that, of course, is equal to 1.5. So that is equal to, or $1.50. I'll just write it like this, $1.50. Now you say, well, gee, that's, I guess, better. But what happens if I don't have the money then? If I still actually need a year? And I say, well, we actually have a system for that. What I'll do is just say that, okay, you don't have the money for me yet. I'll essentially, we can think about it, that I'll just lend that amount that you need for you for another 6 months. So we'll lend that out. We'll lend that out for another 6 months at the same interest rate at 50% for the next 6 months. And so then you'll owe me the principal, $1.50, plus 50% of the principal, plus 75 cents, and that gets us to $2.25. So that equals $2.25. Or another way of thinking about it is to go from $1 over the first period, you just multiply that times 1.5. If you're going to grow something by 50%, you just multiply it times 1.5. And if you're going to grow it by another 50%, you can multiply by 1.5 again. So one way of thinking about it is that 50% interest is the same thing as multiplying by 1.5. So if you start with 1 and multiply 1.5, multiply by 1.5 twice, this is going to be the same thing. $2.25 is going to be 1 multiplied by 1.5 twice. 1.5 multiplied twice is the same thing as 1.5 squared. And you can see the same thing right over here. This is the same thing. 100% is the same thing as multiplying by 2, as literally multiplying by 1 plus 1. So this is multiplying by 2. So you could view this right over here. You could view this as 1 times 1 to the first 1 times 2, I should say. 1 times 2 to the first power, because you're only doing it over one period, over that year. And you say, hey, once again, where is that 2? Well, if someone's asking for 100%, that means over the period, you're going to have to pay twice. You're going to have to pay the principal plus 100%. You're going to have to pay twice what you originally borrowed. If someone's charging you 50%, over every period, you're going to have to pay whatever you borrowed. So that's kind of the one part, plus 50% of it. So 1.5 times what you borrowed. So you multiply times 1.5 every time. And if you wanted to see how this actually related to the interest, you could view this as, so this right over here is equal to 1 times the interest part is 1 plus 100% divided by 1 period to the first power. And I know this seems like a crazy way of just rewriting what we just wrote over here, writing 1 plus 1, but you'll see that we can keep writing this as we compound over different periods. This one right over here, we can rewrite. We can write as 1 times 1 plus 100%. Here, we took our 100% for the year and we divided it into 2 periods, 2 6-month periods, each of them at 50%. 1 plus 100% over 2 is the same thing as 1.5, and then we compounded it over 2 periods. And actually, let me do that 2 periods into a different color. So the periods, let me do in this orange color right over here. And you might start to see a pattern forming. So let's say, well, gee, maybe I have the money back in, and you don't really like this because this is $2.25. That was more than the original $2. So you say, well, what if we do this over every 12 months? I say, sure, we got a program for that. So after every 12 months, after every month, I should say, I'm just going to charge you 100% divided by 12 interest. So this is equal to 8 1/3%. And taking having to pay back the principal plus 8 1/3%, that's the same thing as multiplying times 1.083 repeating. So after 1 month, you would have to pay 1.083 repeating. After 2 months, and this isn't to scale, that actually looks more like more than 2 months, so it's not completely at scale. After 2 months, you're going to have to multiply by this again. So times 1.083 repeating. And so that would get you to 1.083 repeating squared. And if you went all the way down 12 months, so let me get myself some space here. So if you went all the way down 12 months, so 12 months, or I should say from the beginning 12 months, so another 10 months. So what's the total interest you would have to pay over a year if you weren't able to keep coming up with the money, if you had to keep reborrowing and I kept compounding that interest? Well, you're going to have to pay 1.083 to the, well, this is for 1 month, so you could view this as to the first power. This is for 2 months, so you're going to have to pay this to the 12th power. We have compounded over 12 periods, 8 1/3% over 12 periods. Or if you wanted to write it in this form right over here, this would be the same thing as our original principal times 1 plus 100% divided by 12. So now we've divided our 100% into 12 periods, and we're going to compound that 12 times. So we're going to take that to the 12th power. So what is this going to equal to, this business right over here? So we can get a calculator out for that. So I'll get my TI-85 out. And so what is this going to be equal to? Well, we could do it a couple of ways. And this is 1.083. This is repeating right over here. Let's get our calculator out. So we could do it a couple of ways. So let me just write it this way. You're going to get the same value. And I don't have to rewrite this one here. I just did that there to kind of, hopefully you see this, the kind of the structure in this expression. So 1 plus 100% is the same thing as 1. So 1 divided by 12 to the 12th power. 2.613. I'll just round. So approximately 2.613. Now you say, well, this is an interesting game. You've almost forgot about your financial troubles, and you're just intrigued by what happens if we keep going this. If we, here we compounded we have 100% over a year. Here we do 50% every 6 months. Here we do a 1/12 of 100%, 8 1/3% every 12 months, and we get to this number. Well, what happens if we did it every day? So if I borrowed a $1, and I said, well, gee, each day, I'm just going to charge you 1/365th of 100%. So 100% divided by 365, and I'm going to compound that 365 times. And so you're curious mathematically, and you say, well, what do we get then? What do we get after a year? Well, you have your original principal. Let me scroll over a little bit more to the right so we have more space. You're going to have your original principal times 1 plus 100% divided by not 12. Now we've divided the 100% into 365 periods. But we're going to compound it. Remember, every time we have to multiply by 1 plus 100% over 365 every day that the loan is not paid. So the 365th power. And you say, oh, gee, taking something to the 365th power, that's going to give me some huge number. But then you say, well, actually, maybe not so bad, because 100% divided by 365 is going to be a small number. This thing's going to be reasonably close to 1. And obviously, we could raise 1 to whatever power we want, and we don't get anything crazy. So let's see where this one goes. So this is the same thing as 1 plus 100% is the same thing as 1 divided by 365 to the 365th power, and we get 2.71456. Let me put it over here. So then we get, so this is approximately equal to 2, and this approximate is it's a very precise approximation, but 2.7, but my calculator's precision is only goes so far, 2.7145675, and it keeps going on and on. And this is really, really interesting. It looks like as we take larger and larger numbers here, it doesn't just balloon into just some crazy, ginormous number. It seems to be approaching some magical and mystical number. And it is, in fact, the case that if you were to just take larger and larger, if you were to take your 100% and divide by larger and larger numbers, but take it to that power, you're going to approach perhaps the most magical and mystical number of all, the number e. And you could see it right over here on your calculator. They have this e to the x, and I can do that. So e to the, I'll raise it to the first power so you can look at the calculator's internal representation of it. And you see just already doing 1 plus 1 over 365 to the 365th power, we're starting to get really, 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 really close to e. And I encourage you to try this with larger and larger numbers, and you're going to get closer and closer to this magical mystery. You almost wouldn't mind paying the loan shark $E because it's such a beautiful number.
So for such a long video, it takes 11 minutes. And for such a long time, what he did is just to tell us what the E is. Oh my god. So let me tell you, the E is just an constant value. It has a bunch of it has a bunch of numbers for it, but for each number inside of the E, they are fixed. You cannot change it. For example, now I could import the math module, and from the math module, we probably got the E variable out there. Here it is the E, the constant E value. Introduction to the Logarithm Properties. Alright, let's get into it.
Welcome to this presentation on logarithm properties. Now this is going to be a very hands-on presentation. If you don't believe that one of these properties are true and you want them proved, I've made 3 or 4 videos that actually prove these properties. But what I'm going to do is I'm going to show you the properties and then show you how they can be used. It's going to be a little more hands-on. So let's just do a little bit of a review of just what a logarithm is. So if I say that that's not the right. Let's see. I want to change. There you go. Let's say I say that let me start over. A to the b is equal to c. So if a to the b power is equal to c. So another way to write this exact same relationship, and instead of writing an exponent, is to write it as a logarithm. So we could say that the logarithm base a of c is equal to b. So these are essentially saying the same thing. They just have different kind of results. In one, you know A and B, and you're kind of getting C. That's what exponentiation does for you. And the second one, you know A, and you know that when you raise it to some power, you get C. And then you figure out what B is. So they're the exact same relationship, just stated in a different way. Now I will introduce you to some interesting logarithm properties, and they actually just fall out of this relationship, out of this relationship and the regular exponent rules. So the first is that the logarithm, let me do a more cheerful color. The logarithm, let's say of any base, so let's just call the base, let's say b for base. Logarithm base b of a plus logarithm base b of c, and this only works if we have the same basis, so that's important to remember. That equals the logarithm of base b of a times c. Now what does this mean and how can we use it? Or let's just even try it out with some, I don't know, examples. So this is saying that, I'll switch to another color. Let's make mauve my mauve. I never know how to say that properly. Let's make that my example color. So let's say logarithm of base 2 of, of 8 plus logarithm base 2 of, let's say 32. So in theory, this should equal, if we believe this property, this should equal logarithm base 2 of what? Well, we say 8 times 32. So 8 times 32 is 240 plus 16, 256. 256. Let's see if that's true, just trying out this number. And this really isn't a proof, but it'll give you a little bit of an intuition, I think, for what's going on around here. So we just use our property, this little property that I presented to you, and let's see if it works out. So log base 2 of 8. 2 to what power is equal to 8? Well, 2 to the third power is equal to 8, right? 2 to the third power is equal to 8. So this term right here, that equals 3, right? Log base 2 of 8 is equal to 3. 2 to what power is equal to 32? Let's see, 2 to the 4th power is 16, 2 to the 5th power is 32. So this is right here is this is 5, right? And 2 to the what power is equal to 256? Well, let's see. Well, if you're a computer science major, you'll know that immediately, that a byte can have 256 values in it. So it's 2 to the 8th power. But if you don't know that, you could multiply it out yourself. But this is 8. And I'm not doing it just because I knew that 3 plus 5 is equal to 8. I'm doing this independently. So this is equal to 8. But it does turn out that 3 plus 5 is equal to 8. This may seem like magic to you, or it may seem obvious.
Yeah, as far as I say, for this video, what he wanna tell us is this simple rule: log base b of a plus log base b of c equal to log base b of a times c. Yeah, and here's another one. What if we do it in a minus symbol, with a minus symbol? Well, it turns out that we have to do some division. For this case, this number had to be divided by this number. So in the end, you put that fraction into this position, and you are done.
Welcome back. Well, I'm going to show you the last 2 logarithm properties now. So this one, and I always found this one to be in some ways the most obvious one, but don't feel bad if it's not obvious. Maybe we'll take a little bit of introspection. And I encourage you to really experiment with all these logarithm properties, because that's the only way that you'll really learn them. And the point of math isn't just to pass the next exam or to get an A on the next exam. The point of math is to understand math, and so you can actually apply it in life later on and not have to relearn everything every time. So the next logarithm property is if I have A times the logarithm base b of c, if I have A times this whole thing, that equals logarithm base b of c to the a power. Fascinating. So let's see if this works out. So let's say if I have, I don't know, 3 times logarithm base 2 of 8. So this property tells us that this is going to be the same thing as logarithm base 2 of 8 to the 3rd power. And that's the same thing. Well, that's the same thing as, well, we could figure it out. But so let's see what this is. 3 times log base, what's log base 2 of 8? The reason why I kind of hesitated a second ago is because every time I want to figure something out, I implicitly want to use log and exponential rules kind of to do it. So I'm trying to avoid that. But anyway, going back. So what is this? Log base 2 to what power is 8? Well, 2 to the 3rd power is 8, right? So that's 3. And we have this 3 here. So 3 times 3. So this thing right here should equal 9. If this equals 9, then we know that this property works at least for this example. You don't know if it works for all examples, and for that maybe you'd want to look at the proof we have in the other videos. But that's kind of a more advanced topic. But the important thing first is just to understand how to use it. So let's see. What is 2 to the 9th power? Well, it's going to be some large. Actually, I know what it is. It's 256, because we just in the last video we figured out that 2 to the 8th was equal to 256, and so 2 to the 9th should be 512. So 2 to the 9th should be 512. So if 8 to the 3rd is also 512, then we are correct, right? Because log base 2 of
It seems like we're done. Since this video, what he tried to tell us is this rule. I hope you could say it clearly. Never mind, even if you don't, later when we get into a more advanced level, we'll meet those stuff a lot in a single question, in a single, let's say, equation or something like that. And we will need to use those properties to get the results one by one. I really don't know what is a logarithmic product rule or power rule. Let me just get into it.
We're asked to simplify log base 3 of 27x. And frankly, this is already quite simple, but I'm assuming they want us to use some logarithm properties and manipulate this in some way, maybe to actually make it a little bit more complicated. But let's give our best shot at it. So the logarithm property that jumps out at me, because this right over here, we're saying what power do we have to raise 3 to get 27x? 27x is the same thing as 27 times x. And so the logarithm property it seems like they want us to use is log base, let me write it, log base b of a times c. I'll write it this way, log base b of a times c. This is equal to the logarithm base b of a plus the logarithm base b of c. And this comes...
Alright, when I say this, I already saw the result. It shouldn't be that complicated, so we'll just skip it because I don't have time for now. Okay, so let's get into another one. Evaluating logarithm, change of base rule. What is that?
Use the change of base formula to find log base 5 of 100 to the nearest thousandth. So the change of base formula is a useful formula, especially when you're going to use a calculator, because most calculators don't allow you to arbitrarily change the base of your logarithm. They have functions for log base e, which is a natural logarithm, and log base 10. So you generally have to change your base, and that's what the change of base formula is. And if we have time, I'll tell you why it makes a lot of sense, or how we can derive it. So the change of base formula just tells us that log, and let me do some colors here, log base a of b is the same thing, is the exact same thing as log base x, where x is an arbitrary base, of b over log base, that same base x over a. And the
this is another quite new idea to me, I guess. I've never really remembered this formula before. I nearly used it before. So maybe that's another reason why I cannot solve those complicated equations. Well, one thing good about the MAC machine is that you can always put something into your notebook and you do not worry about losing it because it will save it automatically and you can later on working on it. Solving exponential equations with logarithms. Alright, let's get into it.
Solve the equation for t and express your answer in terms of base 10 logarithms. And this equation says 10 to the 2t minus 3 is equal to 7. And we want to solve for t in terms of base 10 logarithms. So let me get my little scratch pad out, and I've copied and pasted the same problem. So I'm just going to rewrite it. So they have 10 to the 2t minus 3 is equal to 7. And actually, let me color code this a little bit. So 10 to the 2t minus 3 is equal to 7. So this is clearly an exponential form right over here. If we want to write it in logarithmic form, that'll essentially allow us to solve for the exponent. So we could say this is the exact same truth about the universe as saying that the log base 10 of 7 is equal to 2t minus 3. 2t minus 3. Let's just make sure that makes sense. This is saying 10 to the 3 minus 3 is equal to 7. This is saying that the power that I need to raise 10 to get to 7 is 2t minus 3, or 10 to the 2t minus 3 power is equal to 7. So these are equivalent statements. What this form does is it starts to put into a form that's easier to solve for t. Now if we want to solve for t, we can add 3 to both sides. So if we add 3 to both sides, we are going to get log base 10 of 7 plus 3. And this plus 3 is of course outside of the logarithm to make it clear. It's just like that. And on the right hand side, this is going to be equal to just 2t. And now to solve for t, we just divide both sides by 2. So if we divide both sides by 2, we get t is equal to all of this business. Log base 10 of 7 plus 3, all of that over 2. So let me see if I can.
Now we can solve some simple equations by using the logarithm transformation or something like that. That's a good start. But again, I just want to remind you that we still got a long way to go before we say that we are already a master of mathematics. So this is today's learning, and I hope you enjoy it, and I will see you guys in the next one. Bye.